guess I could start, right? It's about time. Okay, so good morning, everybody. So let me start with the final lecture in this series on ab initio calculations in nuclear physics. So yesterday I tried to explain a little bit the way how we can describe simultaneously nuclear structure, nuclear reactions using this approach that I call no-Korshal model with continuum. So it's an extension of the no-Korshal model, which by itself is nothing else than just expansion of the wave function in as a linear combination of harmonic oscillator basis states. But in this no-Korshal model with continuum extension, we add to the a wave function which would be just described, or which would just be this part which uses the expansion in harmonic oscillators. We add to it a part which is cluster-like, and so that then so in this cluster part we have two or more in general pieces. So that will be one wave function which would describe one of the cluster. So I gave this example beryllium-7, so then it could be like an alpha particle, and this should describe, for example, helium-3. And so then this cluster function is then coupled to some channel spin, and then you have the spherical harmonics, which will describe the relative motion between the clusters, and then you have the wave functions of the relative motion of the clusters that you want to determine, and obviously you also need to have the wave function antisymmetrized, so that's why you have to always include the antisymmetrizer. So these clusters are antisymmetrized for the internal degrees of freedom, but we also need to antisymmetrize the nucleons from different clusters. So this is the kind of trial function that I'm using in this calculation. And now physics-wise, let's say this part of the wave function, again, it's just an harmonic oscillator basis expansion, so it's a square integrable basis. So that describes all the nucleons in the same way, but it does not allow to separation of the nucleons, because this is, all the tails of the wave functions are like Gaussians, so you cannot remove a nucleon. But in any case, this part would describe the system when all nucleons come close together, and this part then allows explicitly the separation of the two subclusters all the way to infinity, so you can describe a scattering or reaction involving these clusters. And so this part of the wave function then optimally describe the system when these subclusters get separated, or they get far apart. So then the advantage of having both types of correlations in the wave function is that you get efficient description of the whole system. And then in the end, when you want to use that, you get from Schrödinger equation some generalized eigenvalue problem, and typically the hard part is to calculate these so-called integration kernels, which are matrix elements of your Hamiltonian and also of the antisymmetrizers in these cluster states, and the coupling of cluster states with the composite states. And so, once you do this, then in the end of the day, you end up with some kind of equations which are not that complicated. So these are, the equations for these parts of wave functions that describe the relative motion of the clusters, and all the physics is then hidden in this type of potentials, which depend on the separation between the clusters. And so these potentials are like the coupled channel non-local interactions that characterize the reactions or interactions between these clusters. So this is the equation to be solved at the end. Obviously, this W, as I said, that includes all the physics, including these couplings between these composite states and the cluster states. And so I, at the end of last lecture, I showed you this method that is called microscopic R matrix on the Lagrange mesh, which can be very efficiently used to solve such equations, even if you have, let's say, tens or hundreds of channels And also this is the integral differential equation, and it can be solved very efficiently with that kind of method. So once you solve it, what you get the wave functions. Obviously, you get, for a bound state, you get your bound state energy. For a scattering state, you get an S matrix. So the S matrix then characterizes the reaction. So you can get the phase shifts from the S matrix, you can get the cross sections from the S matrix, and so on. So today I will just show you some examples of what kind of physics can we learn from this formalism. Okay, so this is what I showed you last time, so I skipped that. And so now, let me start with the simplest system that can be efficiently described in this formalism, in this method, and that would be a 5-nucleon system, or scattering of a nucleon with helium-4. So if you look at, for example, neutron helium-4, so then there is a huge gap, between this ground state of this system and the next threshold where something happens, right? So I have to go 17.5 MeV to separate or split the helium-4 into the triton. Okay, so helium-4 plus neutron into a triton and deuteron. So in this energy regime, just looking at the helium-4 plus neutron, helium-4 in its ground state is already a very good description of the system, right? Once you have a higher excitation, you have to take into account that this process can happen, that you can, go from helium-4 plus neutron to triton plus deuteron. If you go a little bit higher in energy, you can get a triton. Okay, then deuteron can disintegrate, and you will get like a 3-body cluster. You have triton, proton, and neutron, and so on. And so at some energy about 20.5 MeV or so, you get also an internal excitation of helium-4 to a zero plus state. Yeah, so this is kind of energetic system for this helium-4 plus neutron, and so this is very favorable for description in this way, because I don't have to worry too much about the internal excitations of helium-4, because there is such a large energy gap, between the next channel. So just limiting ourselves to the ground state of helium-4 and a nucleon will give us a very good description of the scattering of the system. Okay, so here I have an example of the calculation of an helium-4 scattering. So this is the energy of the system in the center of mass. So it's like the kinetic energy of the neutron relative to helium-4 in the center of mass. And here I show phase shifts for different partial waves, right? So for example, this green one is the 3/2 minus partial wave. That means that here the j pi t in this expansion would be 3 minus and t is 1/2. So sorry, 3/2 minus and this t is 1/2. And in this when I'm doing this calculation in this expansion, as I said, here I consider helium-5 eigenstates from the no-core shell model, and here I will have helium-4 in the ground state, and this is the neutron. Yeah, and then I couple that, so if it is p 3/2, so that means that L here would be 1, right? So it's a p wave, so L is equal to 1, and here the channel spin would be 1/2 because this has a 0 plus, and this is neutron has spin 1/2, so this will be s 1/2, and so here you have L equal 1, so you will get 3/2 or 1/2 with the parity minus. Yeah, so the 3/2 is the green, and the black is the 1/2 minus. And so what you see now, the phase shift is increasing rapidly as you increase the energy of the system, and then it actually crosses, you see it crosses 90 degrees. So if phase shift, so hand waving argument, if the phase shift increases and crosses 90 degrees, then we say there is a resonance in the system, right? You can see, so that resonance would correspond to the ground state of helium-5. obviously the system is unbound, right? So that's why we had no bound state in this, and so the ground state is then has a positive energy, but it is still because the phase shift is increasing rapidly. It is still a resonance. That means that the system will stay in that resonance for a while before it disintegrates. Now the black line is the 1/2 minus. So again, it's a rising phase shift. So again, it's one would think it's a resonance, although you can see that now the phase shift doesn't go all the way through 90 degrees. So that means that this would be a much broader resonance, much harder to observe in, for example, in the cross section. And then you have other. Let's say this is the red is the S1/2. So this is the S wave of the neutron helium-4 system. That means here L equals 0. And you see there the phase shift is actually decreasing. So that then corresponds to a repulsion between the neutron and helium-4. And so why is there a repulsion? Is because the Pauli principle does not allow, I showed you this integration kernels, the figures of integration kernels for this particular system, neutron helium-4, and you saw that, there the potential basically between, the S wave neutron helium-4 had this cancellation of these different contributions. And basically this was due to the Pauli principle that in the S wave you would like to basically put your neutron to helium-4, which is ground state, which is mostly in the n equals 0, so that means in the 0 S1/2 shell, which allows you to include only 4 nucleons, right? And now you have the 5th nucleon, and you kind of want to put it into that n equals 0 state, and that is Pauli forbidden. So therefore, you cannot expect any resonance or bound state or anything in such a configuration, and what you get in the end is just some kind of repulsion that really the neutron is not allowed to get there, right? So they just split. And then this blue is a D wave, and so it's 0, so it's like nothing is happening here, except when you get to this very high energy, and then you get something which looks like a sharp resonance. So do you know what it corresponds to? Anybody has an idea? Yeah, exactly. So if I go back to this figure that I had in a sec, okay, so this one. Right? So this is exactly. So I will come to this again. Oh, that was okay. Okay, so now move on. Okay, so now is the same thing as before. But here I want to show you what is the sensitivity of these phase shifts if we change the Hamiltonian. So here the red line is the calculation of, sorry, actually I wanted to say one more thing that I now realize that I forgot. Yeah, okay, sorry, this is important. So here these full lines, this is what I get from the no-core shell model with continuum, and so here I used an interaction which is the chiral N3 law from Enten-Machleit from 2003. So this is a accurate interaction. And so what I did here is I would have hard time to use it as it is. So this was SRG evolved. I told you about the SRG evolution, and I included this three-body induced contribution. So it's NN interaction, just NN interaction, but then I do SRG and I induce three-body and higher body terms, and I include the three-body induced in the calculation. And then I met at some point Rimantas Lazauskas, so he is from Strasbourg, and he does the Faddeev-Jakubowski calculations. And so then he actually started to do, originally this is for more, this is done for 4 nucleon system, but he extended that to 5 nucleons. And so then we discussed, okay, can we compare our results? And so that's what we did. And so his calculation are these points. And he used the same interaction, but bare, without any SRG. Yeah. And so now we compare, and indeed we agree very well in the phase shift. So there is some discrepancy here, but I think maybe he said that he might have a problem with convergence in this particular wave, but overall this is a very nice agreement. So these are completely different methods, and even the interaction is treated differently, right? Because he used the bare and I used the SRG, and still we get the same result. So this is very good that we are able, to really benchmark different methods and convince ourselves that what we do is okay.
Yes, but sorry, it could be that you both have a problem.
Sure.
And that by using two different methods and two different interactions, you compensate.
Yeah, but it's very unlikely.
Yeah, I know.
So I'm not worried about that.
Try with the same interaction, both of you. In that way, it could be a real benchmark.
No, it's the same interaction.
I understood that you said
Yeah, it's the same interaction, but I do the SRG. So I'm doing one more step, but it's mathematically, it's just, yeah, it's the unitary equivalent. Obviously, it's not unitary equivalent because I stop at the three-body induced, and I should have 4 and 5. Yeah, no. Okay, so the thing is that, yeah, I cannot do a calculation with the bare, and he cannot do a calculation with the three-body. So yeah. So we could obviously use something like what you had this problem that Jeremy prepared for the deuteron with the Minnesota interaction. So that's a trivial, simple, soft interaction. So that we definitely could solve both of us in as is. But that's very unrealistic central interaction. So it will give us some very strange phase shifts, and it's not. Yeah, one really wants to compare something which is realistic, which also compares well to the experimental data. So
but then if you don't use the three-body, that
he does not use the three-body. He cannot. He does not. I am.
you switch it off.
No. So now, if I would switch this off, then I would get something completely different, because this is so if you do SRG only two-body, then you violate unitarity. So then I cannot compare to his calculation anymore. So I have to have the unitarity preserved to some extent. So this is not full unitarity, because, as I said, there would be a 4-body induced, there will be 5-body induced, and then I don't include. He doesn't, yeah. I include the 3-body induced. No 3-body, chiral 3-body is not. That's my next slide. But yeah, but this is the benchmark. So as I say, because in his method at the moment he couldn't include the 3-body, so we couldn't compare with the 3-body explicitly. But yeah, so the 3-body is here. So the red line is the calculation where I have the the same 2-body as on the previous slide. And I add to it this chiral 3-body. So this is called this NN plus 3 and 500. So the 500 means that the cutoff in the 3 bodies was 500. And these crosses are like experimental data. So it's not experimental data. This is the analysis of experimental data using phenomenological R matrix. So this is people can analyze. So this was done by Jerry Hale from Los Alamos. So he analyzed cross sections and different observables in the system, and from that, using this phenomenological R matrix formalism, he can get the phase shifts which will describe the experiment well. And so now our calculation, we compare to these phase shifts. And so what you see is then the red line has, as I said, the 2-body plus 3-body chiral interaction. I do the SRG on it, so again I'm including the SRG induced from this. And the blue line is when I switch off this chiral 3-body interaction. So that would be, so the blue line is basically the same what I had on the previous slide, when we did this benchmark with Lazauskas. Yeah, and so what you see now that the yeah, okay, yes, yeah, okay, so yes, so I always use this notation that you have 2s plus 1, so the s is this as here, and then I have the L, and then I have the J, right? So the J is this, L is this, and S is that. Yeah, so these rising phase shifts are the P waves, and this is the S wave, and this is the D wave. So it's L equal to, yeah, and so, okay, so now I think I should have, no, sorry. Okay, so now what you see is that the, once you have I include the three-body force, the phase shift, the split between the P wave increases, the difference between the two red phase shift is bigger, and it's actually much closer to the experimental data than the blue one, which doesn't have the three-body force. So that tells you that the three-body force contributes to the orbit splitting of the P waves, right? So then you have L equal 1, and then your spin could be 1/2 or okay, sorry, the spin is 1/2, but then the total J could be 3/2 or 1/2, and so with this three-body force you kind of increase the difference between those two. Yeah, that is then, so it doesn't look like a big difference, but if you look at the cross-section, it's a huge difference in the cross-section. So now here with this, I'm getting very close to this resonance in the 3/2 minus, which dominates the cross-section. So you see, so there are, the crosses are the data, and clearly this red is much closer to the data, and the blue has this resonance shifted to higher energy, right? So it's broader and at higher energy. So yeah, so it's definitely a much better description with the three-body force. And again, you see the bump here, and that is again, you know, this DT channel that's opening up. Yes.
So how does it happen that the pre-nuclear inclusion shifts the bump a bit further from this?
Yeah. Okay, so it's a good question. And so the answer is that this is not a complete description. What I'm doing is, you know, this no-core shell model with continuum, where here I have the helium-5 from the no-core shell model, and here I have helium-4 plus neutron. But to do this properly, I should, you know, include in my sum here, in the new, I should have also D plus T. And I will come to that. But so here I need to increase my basis by D plus T, because that's the explicit channel that is opening up. If I don't do that, I still describe it a little bit, because I have here this helium-5. But this gives me some, you know, okay, so here it's not visible like a sharp peak, but so the point is, okay, so once I include the DT, it will come down. So this is incomplete description of that peak. Okay, so now I have the same thing, but now for the proton. So before I had neutron on helium-4, now I have proton on helium-4. And so here, so you see it looks almost the same, although the resonance is shifted to high energy because of the Coulomb interaction. And again, so the red line, okay, so now actually here, this is all with the 2 plus 3 body interaction, but now I study the convergence with respect to the number of excited states of helium-4. So I said before that the helium-4 is very tightly bound, so it has a ground state, and the first excited state above the ground state is at 20 MeV, so it's a huge gap. So you know, to get the 0 plus excited state, and then at higher energies, around, I don't know, 22 MeV up to 25 MeV, you get some negative parity excited states. And so here in this calculation, we included, you know, 1, 2, up to 7 excited states, which goes up to 25 MeV of excitation of helium-4. And you see that basically the phase shift don't change as I keep increasing the number of states. And the reason why they don't change is that we have this part here, this helium-5 and no-Korshaw model, which basically includes effects of these excited states. Because that really describes well the 5-nucleon system when all nucleons are close together, and that corresponds to the situation where, you know, I have this helium-4 excited. So that means that even if I use only helium-4 ground state, I still get very good result in this, because it's very much more complicated to have these excited states of helium-4 in the calculation. So that corresponds, you know, here I have this new summation. So here I will have, you know, this alpha-1 that corresponds to the counts the excited states. So so this basis will increase quite a bit. Okay, and then these are the differential cross sections for a particular angle in this helium-4 pp scattering, and the energy is basically at this resonance here. So it's just okay. So sorry, the peak that we see here in the cross section corresponds to, you know, this resonance. And so now to get this right, you really have to make sure that your phase shift goes through the data at the resonance. And I have here the comparison, if you can see that. Yeah, so this gray or brown dashed line, so that corresponds to the situation where I do not include this part. So I would cross out this piece. So this is this helium-5 and no-Korshaw model, and only consider this, and that is for the helium-4 in the ground state. So no, maybe it's even with these, I don't know, 7 states. Oh, I forgot the details. But anyway, so the point is that here I switch off this, and then my phase shift does not converge all the way to the data. Yeah, it's an incomplete calculation, and that then has a dramatic effect on the cross section in the region of the peak, right? I mean, in the resonance, because I am off resonance here. So you see that it's completely off the data. Okay, and so now let's move on to something else. I showed you this figure for helium-6. So this is just no-Korshaw model. Then I said, okay, and why don't we do helium-7 in the no-Korshaw model? And then we get that we see that we get an unbound system, but we cannot say what is the width of this state, or we cannot say anything more than just it seems like it's unbound in this calculation. And so now we can do better, because we have now this more complete expansion of the trial wave function, and so we can include continuum, and in particular we can include the, you know, helium-6 plus a neutron explicitly. So then in my expansion, this would be the helium-7 in the no-Korshaw model. So that's exactly, you know, what I had. What did I do? Right. So this part, right? This part is what I would describe by this wave function. But now I include also helium-6 plus neutron. That means here I have helium-6, here I have a neutron, and then I couple them somehow. And again, these are the phase shifts that I can get from, you know, by studying this n plus helium-6 continuum. And now for the helium-6, now I include not only the ground state, but also excited states, because now this 2 plus is not at 20 MeV, but at 2 MeV. So it's actually important to include that. So here it is, you know, really mandatory to include excitations of this helium-6. So in this part of the expansion, I'm including excited states of helium-6. And then you see, so from this phase shift again, what you see that the ground state resonance is in this 2p3/2. Yeah, so and so that would correspond to the ground state of helium-6. So experimentally it is here. So here experimentally of helium-6 plus neutron, and at about half an MeV above that, you have this helium-7 resonance, which has the spin 3/2 minus. Yeah, so this is the experiment. This band is the resonance with its width, experimental width, and this is what we get from this calculation. Okay, so it's not exactly in agreement with experiment, but qualitatively it very much agrees. So you see very sharp resonance, and definitely, you know, now from this we can calculate the width. So it doesn't exactly agree with experiment, but it's not that far off actually. So that shows you that, you know, for this type of exotic nucleus, one has to do, you know, the proper calculation with the continuum, and then one can learn more about the system. And actually, one interesting thing is that, yeah, so you have these resonances: 3½ minus, 5½ minus, 1½ minus. So this is the 3½ minus is here. This is the 5½ minus, which is built actually on the excited state of the helium-6, or on the 2+ excited state of helium-6. That's why it starts not at 0, but in this energy of 2 MeV or so, because that is where the 2+ is located, right? So this is like the helium-6 is in the 2+, and the neutron interacts with that, creates a resonance. But then there is also this 1½ minus, which is this rising resonance, rising phase shift, and that one was very much controversial because there were several experiments, and each experiment said something different about this. So there was one experiment that said it, you know, it should be at 3 MeV. The position of this resonance. In other experiment it was 3.5, and yet another experiment they found it at 1 MeV, so much lower somewhere here. But then the widths differed very much. So in this first, you know, measurement, they said it should be 2 MeV. In this experiment, they said that the width should be 10 MeV, so that's completely huge. And then in this experiment where they claimed to have it at 1 MeV, they had very narrow, only 750 keV. So anyway, so we did this calculation, and what we get is that's shown here. So what we got was, you know, this position is about 2 point something MeV, and the width is about 3 MeV. So that sort of this calculation agrees with this experiment that was done at Argonne, and disagrees with these other experiments. So basically that allows us, you know, to discriminate between experiments.
This is something that Rogachev last time, or is the last?
Yeah, I think Rogachev is this 15, yeah.
So we discussed this many times. In the end, our conclusion, I mean, our group was that helium-7 basically doesn't exist.
No, but I mean, I guess nobody disputes the 3½ minus, right? I mean, the 3½ minus is not disputed. Oh, don't you talk about helium-9? The helium-9 is much more controversial. But I mean, no, but I think the ground state, there is no dispute here. So the controversy was in this 1½ minus, yeah. But I think it's already now, even on the experimental side, it's settled. But the helium-9 is much more tricky. We have new calculation for helium-9, but then we have some conclusions, but still, you know, I would not bet too much money on the result. But, okay. So now I already showed you this N-helium-4 and this fusion, or let's say this peak corresponding to DT. So let me just say a few more words on this. So this is actually quite an interesting reaction, and very important, and it's actually important for both nuclear astrophysics and also for, you know, experiments that are done here, because one can think that this reaction could be used to generate energy from the fusion. And so there are well-known experiments at Lawrence Livermore National Laboratory, which is called National Ignition Facility. And actually this is the picture front of this National Ignition Facility. So this is Sofia Quaglione. And then there is another experiment which is in France, on the southern France. It's called ITER, right? So this first one, what they do is they shoot lasers on some capsule, and then they want to see in the capsule you have DT, and with laser you want to push that DT together and then create the reaction. And in ITER you will have the plasma of the DT confined in the tokamak, and if you can confine it for a long time with high temperature, then one can also get this reaction. And at the same time, this reaction and its mirror, helium-3 DP, they play a role in the Big Bang nucleosynthesis, so I think it was also covered by Gabriel. And so now, physics-wise, okay, I don't know if you can see this. So this is the experimental situation from the tunnel. You can find it in the tunnel website. And so here is the D and T. This is here is the helium-4 plus neutron. This is the helium-5 resonance, this 3½ minus. Then there is this 1½ minus, which was very broad. And there is the 3½ plus, that's where I had the bump. And this DT is just below this 3½ plus. Yeah, it's just below that. And so now the thing is, because there is this resonance, then this cross-section is very much enhanced. So that's why very close to the threshold you get a resonance. So then it enhances quite a bit this reaction rate. And actually, why it is so interesting? First, there is this resonance which enhances the rate, and second, you get a huge amount of energy. Yeah, when you combine the D plus T, you get 17.6 MeV, because it was split into helium-4 plus neutron, so you get this 14 MeV neutron and 3.5 MeV alpha particle. So this is a huge gain, and so then people think that it could be used really to generate energy, as opposed, for example, to the fission of uranium. Okay, so now, so this is the Big Bang nucleosynthesis. So again, this was more covered by Gabriel, but I just want to show you. Here you have DT and helium-4 and D helium-3 proton helium-4. So they are the network of reactions that is relevant for the Big Bang. Okay, so I had this figure. This is this benchmark. So this is my peak of the corresponding to this DT resonance, but this calculation is done only with neutron helium-4. So I have helium-4 plus neutron, and I have a peak because I included these no-core shell model states of helium-5. So this would correspond to the 3½ plus state, but this is, as I say, this is in a harmonic oscillator basis, so it's like a confined, state. So it does not allow the separation for the DT. So this is only in the helium-4 plus neutron. But now, if I include also the DT, then I get a different phase shift. Okay, so now I'm zooming in this region. Yeah. So what I have here, it starts at 17.8, you see, so it's somewhere, here. So now obviously this peak will shift. Once I include the DT, then the peak will shift. But what you see now, this is this D wave here, so it's this. So now it changes a little bit the shape, so it doesn't go all the way up and down. And now in this other phase shift is an S wave, but now this is between D and T. Yeah. So what does it mean? So I have the deuteron and the triton. So the triton has the spin 1/2, and deuteron has the spin 1, as you learn in this exercise when we calculated the phase shift, sorry, the binding energy of the deuteron, right? So you have triton, which has the spin 1/2, and then you have the deuteron, which has the spin 1, right? 1 plus. This is 1/2 plus. And so now, if you align the spins, you can get 3½ plus, right? You can have 3½ plus, but also you can anti-align them, and then you will get 1/2 plus if you have the spins opposite, right? So this is spins go like that. But then obviously you can have different orbital momentum, but this is for the S wave. Yeah. So what I have here, this phase shift corresponds to the S wave between the triton and the deuteron, and the spins are aligned, that's 3.5 plus. And so that's exactly where this resonance is. You see that the phase shift goes up all the way through 90 degrees. It's a very sharp resonance. But now this is a transfer reaction. So in this, okay, obviously you can just scatter, but you can also now transfer to this helium-4 neutron, and that will go into the D wave of helium-4 and neutron, right? So now this is in the D wave, so that is here. So the S wave, helium-4 plus neutron is here, but that one has the spin 1/2, so you cannot get, because you have to conserve the angular momentum, right? So you go from 3.5 to 3.5, but you change your orbital momentum from S to D, and obviously you change your partition of the mass partition. Anyway, so then in our calculation, what we show here is that the mechanism of this process is that we go from dt in S wave, which spins aligned, to N helium-4 in the D wave. And in general, so this is now this process is again sensitive to the details of nuclear interactions. You change the orbital momenta, so you can imagine that the tensor force will play a role, and also the free body force will play a role. So it's a very complicated process that needs to be described with a realistic interaction. And now what we can do with this, we calculate this phase shift and so on, calculate the S matrix, and from the S matrix we get the cross section. Okay. Yeah, so this thing that was described by Gabriel. So again, this is the cross section, and this S factor explicitly takes into account the effect of the Coulomb interaction. So this has a very dramatic effect of the cross section, and so now if but this is known. This is just the effect from the interaction. So if you then multiply your cross section by this factor, you will get something which is much more energy independent. Obviously, in this particular reaction, the S factor is not like flat, and the reason is that we have this resonance. Right? So because there is a resonance, not only the cross section has a dramatic dependence on energy, but also the S factor. So now this dependence is due to the strong interaction, not due to. And so what we show here, okay, so the red are a zillion of data. This was measured many times because this is such an important reaction. And then the blue and these are the calculations in Korschel model with continuum. And this is the angular distribution. Okay, this is for the forward angle, differential cross section for the theta equals 0 angle. And again, calculated in our approach compared to the data. And so I just want to mention, so when we do the calculation, you get this green line with this, this interaction that I showed before, this NN plus 3 and 500. So we get the green line, so it's close, but it's not exactly on experiment. So why it's not exactly on experiment? It's because the interaction that we have does not put the resonance exactly where it should be. Yeah, so you can imagine that with your, chiral forces, you cannot expect a precision, FU keV. So this really depends on FU keV to get this right. And so now it looks like it's hopeless that, how can we get an interaction that will give us this action within a few kV? So that's unlikely to happen, even though the interactions are good, but they are not that good. So, but then what we can do is very simply, use a little bit of phenomenology with this. And so now these are my equations for the, this NCSMC. And what I can do now, I can, I have here these eigenenergies that I get from the no-Korshal model. So I diagonalize no-Korshal model Hamiltonian for this helium-5 here, and I get some energies. But what I can do, I can then treat them, as a stable parameter. So I can change this number, one number here only, a little bit, just really a few keV. And I keep the rest. So I keep the wave functions, everything else I keep. And that allows me then to shift my cross-section, just to the right position. Because I get now the position of the resonance where it should be, and so then magically my cross-section also agrees with the data. But what is now, okay, so this is now we describe this data that has been measured so much. So that it's nice, but okay, maybe we want to add something more. And so here we actually can learn something more. We can look at what happens when we have a polarized fusion. So the polarized fusion means that we will have the D and T aligned, so you can imagine that you can put your deuteron and the triton in the magnetic field and polarize them. Yeah, and so now when they are polarized, the cross section will change, and the reason why it changes is because this fusion goes to this 3½ plus. So it happens only when the spins are aligned, and when they are anti-aligned, you will get no resonance. So basically, then you will get no fusion. So only in this channel. And so now, if you put your nuclei into the magnetic field, you align spins, then you enhance your cross section. So this is known. However, to do experiments like that is extremely difficult. So it's actually has not been really measured very much, or maybe not at all. If there were some measurements that was done with helium-3 actually, which is easier to deal with. And so now what we can actually do the calculation, because we have everything, okay, so we can always do calculation, right? So we can do whatever we want with these nuclei. So we did the calculation for the polarization, and you get indeed, you see that you enhance. So this dashed lines are the calculation for the unpolarized compared to some analysis of the data, and the blue is when we polarize D and T, with some realistic polarization that can be experimentally achieved. And you get enhancement of the cross-section by about 30–40%, which is nice. And also, it's not visible here, but actually now the peak shifts a little bit to lower and a lower temperature, right? And that is advantages. So if you polarize, then you can actually achieve the fusion at slightly lower temperature, which again is very good, because it's not so easy to keep this plasma at such high energy. So what I have here is the reaction rate, that is the mean value of the cross-section times the velocity. And so this was again derived by Gabriel. So you get this Boltzmann factor. And here you get this factor, which is coming from this Coulomb part, right? So you get this Gamow window, but now remember that the S is not flat. It's not like constant. Here it is much more complicated because of the resonance. Yeah. And also, what is interesting with this, that from once you have a polarized cross section, what happens that your outgoing helium-4 and neutron actually then will not go isotropically, but they can actually preferentially be emitted with a 90-degree angle. And so that, again, one can take an advantage of that. Or let's say that is useful because you can set up your your tokamak, whatever, I mean, that you can efficiently capture the alpha particles so that they will reheat the plasma and so on. Yeah, there is nothing unphysical about it. I mean, okay, so that's not ab initio anymore, right? I'm just tuning my number. But it's a very small change. I'm changing one number, out of the zillion that I have in all this business, right? So it's, as I say, I mean, I have an eigenvalue for this eigenstate, and I change it by, FU keV. I mean, the interaction is not perfect, right? So if you would use, if you do atomic physics, then you know your interaction exactly. That's the Coulomb interaction. Here, this is the, nuclear interaction. So, I discussed before, all these chiral expansions, zillion of parameters, and, so this is already pretty good that you can get. Yeah, but this is very important. Okay, so it's a correction, as I say, I mean, it's a very small correction, but if you really want to compare to the data or predict, then it's really important to do this. So now, this makes a big difference in the description of the data. So I showed this helium-7, for example. So there was no adjustment. So then it doesn't agree exactly with the data, but it agrees qualitatively. So I can make qualitative statements. But here I really want to make a quantitative statement. Yeah. Because I want to predict, for example, this polarized cross-section, and I want to say, okay, this is my prediction for the real system, right? So now I want to be precise. So then I have to make sure that my resonance is where it should be. Otherwise, it's no. Okay, so you can also do that, but then you can say, why should I tune this one and not something else? So people use different things to tune. So in these interactions, typically we prefer to tune just in the nucleon and 3-nucleon system. Sometimes 4-nucleon system, for example, radius of helium-4. Once you go to heavy nuclei to tune your interaction, then that we can say, okay, now what is your predictive power, because you adjust your interaction to oxygen 16 or something. But still, you would adjust to oxygen 16, not to this. This is such a tiny detail that. Okay. Okay, so maybe I will skip. Okay, no, I will not. Okay, but maybe let me go on. Okay, so now I go back to my. Okay, this is this Big Bang reaction network, and so now let me talk about the lithium-6. And so now again, so this was covered by Gabriel, so I will not go into that, but. In general, this Big Bang it produces the light nuclei, and that basically the predictions basically agree with what is observed. Although for lithium-7 you are predicting like 3 times more than what is observed. But then there is also lithium-6, which is underproduced by 5 orders of magnitude. So that's like a big discrepancy, but then people say, okay, we cannot really measure that, so maybe the measurement is wrong. So, okay, just as an intellectual exercise, so we can look at this, if we can learn something about how the lithium-6 is produced in this scenario, and actually the production is from the alpha capture. So you have alpha and deuteron and captured to lithium-6 with emission of a photon. So now in our no-Korschalm model with continuum, we calculate lithium-6, and then we can say something about this reaction. Okay, so similarly as I showed you neutron helium-4, so now I go to a more complicated system. So now I study deuteron plus helium-4. It's actually infinitely more, not infinitely, but very much more complicated. And the reason is that the deuteron is so weakly bound that it easily can separate into, so deuteron obviously is bound by only 2.2 MeV. as you could have learned from this exercise. So now if I do D plus helium-4, so at very low energy I already must see effects of a separation of deuteron into proton neutron plus helium-4. So now to include, obviously in our expansion we could also include proton neutron helium-4, then I will have 3-body cluster here, but that is so much complicated that we have not done that. So in this calculation what we did is we treat the deuteron in the ground state, but we also include its virtual excitations, or let's say excitations that we get in the harmonic oscillator basis. So this is kind of poor man treatment of this proton-neutron continuum, but at very low energies it's actually quite reasonable. So anyway, I will not go into technical details, but I just want to show you this calculation that we did for the d-alpha scattering and structure of lithium-6. And so maybe on this figure, so this is just the experimental spectrum of lithium-6. Again, you can calculate this with this big stick code that I gave you. So some of you did it. So then, the ground state is 1+, then you have 3+, and then you have the other excited states. And experimentally, only the 1+ is bound. The 3+ is already a resonance. And so now, so this is experiment, and here I have no core shell model calculations. And so this one is just with the 2-body force, also although I include this SRG-induced 3-body. And the red line is the calculation with the, when I include the 3-body, Kairos 3-body. And this column is then extrapolation of the red. So this is done at finite Nmax. So I don't know, it was Nmax 10 or 12, maybe Nmax 10. And then you extrapolate, and this is what you get by extrapolating. So obviously, and the width is then uncertainty in the extrapolation, so the higher you go, the more uncertain it is. But for the ground state, you get a pretty good extrapolation. And on the right-hand side is now the calculation with no Korshal model with continuum, which means that I include here, the alpha particle and the deuteron. And for the deuteron, I include also these virtual excitations of, which go beyond just the ground state of the deuteron. And you can see now that, so this calculation actually, okay, so this is definitely a superior calculation because it has also much bigger basis and describes properly these unbound states. So for the bound state, we get the same result that is to be expected. Yeah, so basically the same energy from the no-core shell model extrapolated and from this NCSMC. For the excited states, you see for the 3+, it's very close. However, from this calculation, we can get the width, while from this calculation, we cannot. So this now corresponds to these phase shifts. So you see that this sharp phase shift, this increasing phase shift corresponds to this sharp resonance. Yeah, so this is this corresponds to that. And this one would be the 2+, so is this one. And again, the blue is the calculation without the Kairos 3-body force, and the red is with the 3-body force. So it's a huge difference. Again, spin orbit changes quite a bit if you include the spin orbit force, so if you include 3-body force. So here I have, if you can see it, so 3+ is this, 2+ is this one, and 1+ is this. NCSMC is not extrapolated. Yeah. So I don't know how I would. Yeah. But this is much bigger basis. So let's say Nmax is the same as here. Let's say 10. But then you have all this other continuum contribution. So it's a much bigger basis. Yeah. So my clusters are described in Nmax 10, but there is a relative motion between clusters. So it's a much bigger basis. Yeah. So it converges much faster. I don't know how. Okay, so I could extrapolate the energies, but I know phase shift I cannot. But anyway, yeah. So this is, and now if I go here, so this is now the blue is without the 3-body force, and you see, okay, it's quite a shift. And if I go, so you see the difference. So basically, this is again the spin orbit splitting. So these are all D waves. So these are all D waves. and so they differ in the, how the spin is coupled. So it's 3 plus, 2 plus, 1 plus, so they are much more separated if we have 3 body force. And this is the cross section. So, okay, so this is the differential cross section at some particular angle. This is the energy of the alpha particle or the deuteron, and you see, so now you have this peak, so that would be the 3 plus, yeah, and then there is a 2 plus is here, and the 1 plus, that's that one. And so now why it is off, right? So it is off because our resonance is not where it should be. So if you look here, right, so this is the calculated 3 plus, and this is the experimental 3 plus. So there is about 200 or so, or 300 keV difference. So now nothing is tuned. So this is just as is, from the chiral force. And then the price to pay is that, you miss the resonance. So this is these 300 keV or so difference. But the rest is pretty good. Obviously, now I could do the same game. I mean, I could adjust, and then I would be on top. But here, we just wanted to see the qualitative, what the chiral forces can do, and that tells us. And so the overall picture is pretty good, but the details are missing, right? But then if we go off resonance, so these are energies which are not at resonance positions, and we get a very nice actually cross section for the d alpha scattering. So these are the angular distributions, right, for different angles of the deuteron compared to experimental data. So I think I was surprised that it's so good. Okay, and so now we can also analyze the wave function that we get from this. So we looked at the ground state of the lithium-6, and then we can look at the so-called asymptotic normalization constant, so that we have the wave function of the d alpha, or the lithium-6 in 1 plus state, the d alpha, and then we can look at so this normalization constant tells you. Okay, so maybe I don't know if I can simply describe that. So your wave function, you have the alpha d. So once they separate, then the wave function would be like a Whittaker function, which will depend on, okay, let's say kr. So the r is the separation, and then there is this okay, some normalization constant, asymptotic normalization constant. So basically your wave function for r going to infinity will be given by the Whittaker function, or if there is no charge. So in this case there is charge, but for no charge, you have minus e to the minus kr, I guess, divided by r, right? So this is the asymptotic form of the wave function for the bound state. So if you have charge, this is the Whittaker function, and then this number that multiplies this tail is called asymptotic normalization constant. So you can directly read it off from the wave function. So we calculate wave function, and then we can compare to this asymptotic solution that we actually also use to properly calculate the cross sections and so on. And from that you can read off this parameter. And you have one in the S wave when the alpha d is in the S wave, and the same if alpha d is in the D wave, you get this C2. And so now why is it interesting? So you see this can be measured, and there were 2 experiments. Okay, here I have some references, and they get some completely different C2 values. From these measurements. I mean, okay, sorry. This is okay. So this is the C2 is here, and then ratio. So in one of the experiments they measured really the C2 and C0, and in the other experiment they only measured the ratio of the C2 to C0.
But maybe for the students, they cannot really measure that. They measure something else.
Okay. Yes. No. I agree. So, Yeah. Okay, but I must say I don't know how they measured. Okay, so they measured some peripheral.
Sections.
Yes. Yeah.
They compare the experimental value to some model.
Yes.
And what they believe that what is the parameter that puts one on top of the other is
Yeah. Okay, yeah, you are right. So this is definitely model dependent, but I think it's still a solid. I mean, they can confidently determine this. And so the point is that there are two experiments where they extracted that and they differ in the sign. And so then we did the calculation, and we can clearly, our result definitely agrees with one and disagrees with the other. So I think this calculation is not perfect, but it's still very reasonable, and so I think I can say that this is the good value. But then I talked about this, yeah. I finished the slide, and then we have the break. Okay, so now I talked about this lithium-6 puzzle in the Big Bang, and so now this cross section at the so now we want to have the S factor of this. So the reaction is this capture, right? So I had it before. Let me just write it. So here what I want is I want the let's say I want the deuteron, alpha, gamma, lithium-6, right? So this is the cross section to be that needs to be determined at very low energy, which is relevant to the Big Bang energies. Yeah. So one can measure it very well at high energies. So that is shown here. There are some points, and you have the peak for the 3 plus. So it can be measured very well at this energy. But for the Big Bang, you really need to go somewhere here, and that is much more difficult. And so you see there are some data which are pretty high, and there are new data. So this is from Luna, so this is here in Italy, in Gran Sasso. And so they really measured this very carefully at very low energy. So this is very recent data, and they are much lower than the old calculations. But then one can also do calculations. And now it turns out that this S factor here is basically determined by this asymptotic normalization coefficient. So by just this C0, so that's this ANC that multiplies this Itaker tail. So basically these numbers are just determined by C0. So I must say at this point we have not calculated directly this, but we determined C0, and now there are formulas that you can actually use. So Mohamed Janov is one of the experts. He had done this calculation, and then you can plug in your C0 and you get the cross section or S factor. And so our result really sort of is in this ballpark down here, which also agrees with this this new measurement from Gran Sasso. And basically this means that this cross section is very low, and that produces very little of Big Bang. So now it depends what you believe. So so there were these claims that say that lithium-6 in this metal poor stars is like 5 orders of magnitude more abundant than what this predicts. But then other people would say, okay, this is not a good measurement, so they don't really see lithium-6, so there is no problem. Yeah, so it depends. So anyway, so the calculation then basically tells you that there is like very little lithium-6 produced in the Big Bang. Okay, so I think this is a good place to stop. Let's have a break, and then I will finish. Okay, so in this last half an hour or so, let me show you a few more examples of the calculations in this formalism, and after that I will conclude. Okay, so let's move on. So you may be familiar with the beryllium-11, which is a very kind of interesting nucleus. So why is it interesting? Because there is something which is called a parity inversion in its ground state. So this has been known for like 50 years. And the question is, how we understand it theoretically. So what it means is that, okay, so this is a nucleus which has 7 neutrons and 4 protons. And so now if you just, imagine the simple shell model picture. So you have, the 0s 1/2 shell, 0p 3/2 level, 0p 1/2, 1s 1/2. So if you have 7 neutrons, so you put 2 of them in the 0s 1/2, 4 of them in the 0p 3/2, and now you have the 7th one, right? And so now what you expect? You expect that it should be in the p 1/2, and so the ground state of this nucleus should be 1/2 minus, right? And so now if you look at carbon 13 or oxygen 15, which have 6 protons, then indeed the ground state is 1/2 minus. However, in beryllium-11, where you have only 4 protons, so you have 2 protons in the 0s, 2 protons in the 0p, then somehow, for some reason, the ground state is not 1/2 minus, but it's 1/2 plus. So now it's like the neutron is sitting up here rather than here. So the question is, okay, can we describe this in our formalism, in our ab initio calculations? Obviously, there are many calculations that have been done, and then try to understand it, and so everybody is looking at it from different angles. So yes, so you can look at it that way. So again, so the question is how okay, so maybe let me come. I will try to explain, or to visualize it maybe better. So that's correct. Yeah. But okay, but then you say, okay, that then the energy should be lower because of that, which is probably correct. But then you have to also ask the question, why in the carbon 13 it's not closer, right? Or so the point is that there is this change, right? So this picture is pretty good. I mean, this shell model picture, is quite reasonable picture. So you are absolutely right about the centrifugal barrier and so in this system that's what is going on. I mean, there is some you get some halo-like structure of the beryllium-10 and the neutron in the S wave. But still, you want to understand, why it's happening here and not in the other nuclei, or Okay, so as I say, I mean, there are many approaches that want to understand this. So Enrique, they published also recently a different type of calculation that also tries to understand this system. So one has to look at from different angles and try to figure out what's going on. So it's clear now that from this ab initio point of view, definitely one has to include the continuum, because this is such a weakly bound system. So here you see the experimental situation. So this is the beryllium-10 plus neutron. So it's this ground state is bound by only half an MeV. And then there is the excited state, which is 1/2 minus, which naively one would expect is the ground state, and that is bound by only 180 kV. So it's extremely weakly bound system. And then obviously everything else is then some resonances that are unbound. So now, just by looking at this, it's obvious that describe the weakly bound systems, one should better take into account, properly the effects of the continuum, and also we would expect that once we are looking at this kind of fine details, that we should have a pretty good Hamiltonian to do this. So presumably the three-body force also will play some role. And now I want to say that so the mirror of the beryllium-11 is nitrogen-11. So the beryllium-11 has 4 protons and 7 neutrons, and nitrogen-11 has 7 protons and 4 neutrons. So it's a it's a mirror. You switch the protons and neutrons, and so now nitrogen-11 can be studied. So it's bound. So beryllium-11 is bound. Nitrogen-11 is not bound, unbound. But one can study easily, or not easily, but still, the scattering of carbon-10 on proton and learn something about nitrogen-11. While for beryllium-11, you cannot really scatter beryllium-10 on neutron, right? You don't have any neutron target, and beryllium-10 is, radioactive, so you cannot have a target from that. But you can study carbon-10 on proton and learn about this mirror of beryllium-11. And actually, what is nice that at Triumph, they produced the carbon-10 beam quite recently, and so they then proposed an experiment to measure carbon-10 on proton, and with a new facility which is called IRIS. And this was actually the first experiment where they reaccelerated the carbon-10. So this was quite interesting. And so then I was discussing with experimentalists, and we thought, okay, this is a very nice testing ground for nuclear forces. So let's just, you can measure and I can calculate, and let's compare. And so that's what we did. And so now, so we did these calculations, as I say, in parallel, the beryllium-11 and nitrogen-11. And so now for this nitrogen-11, what I do is I want to calculate the system using the, this would be the nitrogen-11 no-Korshaw model wave function. And then I will include the carbon-10, that is this part here. I have carbon-10 in 3 states, 0 plus, 2 plus, and 2 plus. So the carbon-10, okay, I don't have it here, but so the you have the ground state, right, 0 plus, and then at about 3 MeV or so, you have a 2 plus, and then somewhere at 5 MeV you get another 2 plus. So we include that in this cluster expansion, and then we have obviously proton here, right? And now for this nitrogen-11, these states here, so we included quite a few, so at least 4 negative and at least 3 positive parity states in this type of expansion here. And this shows again the phase shifts. These are only p-wave phase shifts. This would be the 1/2 minus, 3/2 minus, 5/2 minus, 3/2 minus. And one can see some of them in experiments. So this is 1/2 minus. I don't know where this is. This is 5/2 minus, and another 3/2 minus should be, this one is the 3/2 minus, yeah. And what I show here is that how the phase shift change if I change Nmax. So in this calculation, we could do up to Nmax 9, and you see that for these, at least, it really doesn't change at all. For this one, there is some change, because also the excitation energy of this 2 plus states is changing in that calculation. Okay, so now we can solve this. So we get the phase shift, we get the S matrix, we get the cross section, and so here I have again. So this is the example of the phase shift for the carbon-10 plus proton. So this is this 1/2 minus. This is the 3/2 minus. This is the S wave 1/2 plus. There is the D wave 5/2 plus. So this, and I don't know if you can see it. So I have here 2 vertical lines. So they correspond to the energies where the experiment was done at Triumph. So they measured at 4.15 and 4.4 MeV. So these are these 2, and actually, so we discussed like where they should measure, And so I thought, I did some calculations, and I thought, okay, why don't you measure around this 3.5 minus resonance? Because I would expect that the cross-section will change quite a bit in that region. So that's what they did. So there was some proposition where this, based on the previous experiments, what this 3.5 minus should be. And so the idea was they would measure just below and just above. So also I would have preferred, if they could measure here, but that was not possible from experimental point of view. So they couldn't go so low, so they needed at least this energy. Obviously, they could also go a little bit higher, but that's more complicated for the calculation. So we just wanted to select some optimal balance. And anyway, so this is what they measured, and this is the calculation of the differential cross-section at the energies of the experiment. Yeah. So this is the calculation where I used just the chiral two-body force, right? Just the chiral two-body force, and I got kind of dip. So then I include the three-body force in the calculation, and now I get a completely different differential cross-section. Yeah, you see now no dip, but it's kind of very much flat and decreasing at these angles. And then they came with the data, and the data was just going in the wrong direction. So it was kind of disappointing. So I said, okay, what's going on here? How is it possible that the data is in completely different direction than my calculation or my best calculation? And so obviously we're a little bit worried. So one thing is you can say maybe they didn't measure well, but they kind of were convinced that they measured well. So maybe I should check my calculations. Okay, so now I go back to beryllium 11, because in beryllium 11 you have much more knowledge about the levels, right? So now I use the same interaction that I had for this on the previous slide for the carbon 10 on proton, and so I use the same interaction here, and I do a comparison to the beryllium 11 experiment. And you see, so this would be just the no-core shell model. I increase the Nmax, the size of the basis, and you see the convergence is extremely poor, right? This is because it's so weakly bound. You have to have a huge Nmax to get anywhere close to experiment. And you can also see that now, even in this biggest space, I have the ground state 1.5 minus, and the red is 1.5 plus is much higher. But at the same time, it's falling rapidly, so now I cannot really say anything. So the 9 is for the positive parity, 8 is for the negative parity. So I mix both parities in the figure. Okay, so this is obviously a completely unsatisfactory calculation, but that's why we are doing, this more sophisticated one. So just now, if I used only the clusters, so I would just use, this part here. So the first calculation is that I used this part, right? This was no-core shell model. The second calculation is I used only this part, where I have the beryllium 10 in the 0 plus 2 plus 2 plus, and beryllium 11 in some, only the beryllium 10 in 0 plus 2 plus 2 plus. So that's this part, or this expansion here. And you see now I get actually pretty stable results, but they are, these states are unbound with respect to neutron beryllium 10, or maybe the black one, the 1.5 minus, is barely bound, 1.5 plus is unbound. But again, to have this calculation converged properly, I would have to include many more excited states of beryllium 10. So I'm including only 3, so this is incomplete. So, but now I mix both these calculations together. That means I do this plus that. And then I get much better reasonable result. So that is shown here. However, you see that the black line, which is 1.5 minus, agrees with the data, but it's the wrong ground state. So it's the 1.5 minus is the ground state here, and 1.5 plus sits at the threshold. So while in experiment is bound by half an MeV. So again, it shows you that the calculation doesn't do well. So it does well for the 3.5 minus, for the 1.5 minus, but not for the 1.5 plus and 5.5 plus. You see? And so now the question is, why is that? So maybe we should look at some, details of, let's say, let's change the Hamiltonian. So this would be again, so this is the experiment, and this is the calculation when I switch off the 3-body force, only 2-body force. And you see now I clearly get this wrong, right? 1.5 minus 1.5 plus, 3.5 minus 5.5 plus. So now I add the 3-body force, which is what I had on the previous slide. So this is the calculation I had on the previous slide. So this is better, but it's still wrong, right? So now the 1.5 minus is where it should be, 3.5 minus is where it should be, but the 1.5 plus didn't change, 5.5 plus didn't change. So this is not good. And so now we thought, okay, what we do next? And so now there was a new interaction that was derived in Oak Ridge, which is called N2LO SAT. And what they did, because we knew already that this particular interaction gives you very small radii and very much overbinds heavy nuclei. So if we go to medium masses, to calcium and beyond, this interaction gives you too much binding and too small radii. So that's not satisfactory. And so because in Oak Ridge they do coupled cluster calculations and they are interested in heavy nuclei or medium mass nuclei, they wanted some better interactions. So what they did was that they were doing themselves a fit of this chiral interaction. But when they were fitting, they included not only the 2-nucleon phase shifts and the deuteron and the 3-nucleon binding energy, but they also look at helium-4, which is okay. But then they also looked at like carbon-14, oxygen-16 that they calculated in the coupled cluster, and in particular on the radii. So they looked at these observables as an input into their fit. And in the end, they got much better description of the radii with this interaction. So it's called N2LO SAT, and that gives very good radii for medium mass nuclei. So then we decided, okay, why don't we use it for beryllium-11? And this is what we got. And you see now there is a very dramatic change for the positive parity states. So now you see that my 1.5 plus goes down quite a bit, and it sort of is where it should be. So the 1.5 minus is a little bit lower, but in the end, anyway, so it's much better than this. And you look at the 5.5 plus, yeah, it's a huge shift, and just where it should be. So that's very nice. And so now with this force, this new force, which has some knowledge of the medium mass nuclei, or at least I don't know, radius of carbon-14, radius of oxygen-16. It gives a much better description of beryllium-11. I think the reason is that the density, the radius is bigger, the density is getting, let's say, more spread out, and that has a positive impact on the description of these positive parity states. So with this, we actually can get the best result. We also predict this 9.5 plus low-lying resonance. And okay, so with this is the best. And so now if I go back to this calculation of the cross-section, so now I include this N2LO SAT, and I get this blue line. So it's not exactly on the data, but you see that the shape now agrees with the measurement at Triumph. So that's quite interesting. And now if I just would scale it, then you see that basically so the shape agrees with the data, so that's good. And so now understand why there is such a difference in these cross sections. One can just look at, so basically the cross sections are very much determined by the two resonances in that region, the 5.5 plus and the 3.5 minus. And you see, if I have just a 2-body force, the 3.5 minus is below 5.5 plus. When I switch on this 3-body force, this 3 and 400, I get the 5.5 plus and 3.5 minus basically in the same spot. And when I use this N2LO SAT, my 5.5 plus go below the 3.5 minus. This is which is found in beryllium-11. So this is the most realistic case. And then indeed I get a cross section that is in the best agreement with the data. So this is all chiral, right? So it's, yeah, so both these calculations with this NN3N400 and N2LO-SAT, so they have the same type of three-body force. Yeah, so the two-body force is different. This one is higher order, N3LO. This is only N2LO. The three-body force is the same order, the same form. However, the parameters are not the same because they fitted the parameters differently. And so there is a change in the one of the parameters really has the different sign, and I think that is the one which actually made all the difference. But okay, so there are several parameters which changed. Yeah, yeah. Okay, so yeah, so if I would redo now helium-4 and helium-4, this helium-5 scattering, I will actually get worse result with the N2LO-SAT. And the reason is, actually, one can understand this very easily. The problem is that with the N2LO-SAT, the two-body force is only at N2LO, a lower order. And they didn't do very well in the fitting of the phase shift. They fitted only low energy phase shifts. And when you don't have higher order, you cannot fit very well P waves, and the P waves impact the spin orbit splitting. So in my helium-5, there is P3 half, P1 half. And it's important to have correct spin orbit in the both two-body force and the three-body force. And now with N2LO-SAT, they cannot get correct spin orbit in the two-body force because they don't have enough low energy constants to fit the NN phase shifts in the P waves. Yes, it plays a role, but the biggest problem that we had for the 1/2 plus is really, I think, it's really the density, the size, yeah, and that's what makes the difference. So this interaction has deficiency in the spin orbit of the NN, but it's good in the density description, and I think it's because the three-body force has one of the contacts is actually repulsive, which then pushes the nucleons further apart, while this one has the contact attractive, which then makes it more dense. So I think that's sort of the hand-waving argument why the P1 half. Right. Okay. So then, where is the P1 half? Yeah, it's this one. Yeah. So in this case, it's not such a dramatic. Okay. Sorry. So there. Yeah. So no. But the difference between the 1/2 and 3/2 minus, that's affected. Yeah. It is affected. So it's pushed further. Okay. So there are two things. One is that the splitting will be higher here. So, and the other thing is that the positive polarity go down. Okay, so, yeah. Okay, so just maybe I can show this. So in beryllium-11, there is also what is known is that you have these two bound states, 1/2 plus, 1/2 minus. And there is a very strong E1 transition between 1/2 plus and 1/2 minus, and it's actually like one of the strongest measured. And so this is the experiment, in these units. And so now, if we would do just the no-Korshal model for this E transition, then we get basically 0, which is not surprising because this E1 will be very much determined by the tail of the wave function, which in the no-Korshal model we don't have. I mean, it's just suppressed. While when we include the continuum, beryllium-10 plus neutron, then we get a number which very much is in agreement with the data. And again, you can understand this from this figure. So this is, the beryllium-11 ground state that we calculate, the wave function of the ground state. So this is so-called cluster form factor or spectroscopic function, where when I overlap my beryllium-11 ground state with the beryllium-10 plus neutron as a function of the separation of the. So basically, I'm taking now, this thing here, and overlapping it with my with my calculated eigenstate 1/2 plus. That means, when I calculate this, so I will overlap it with this component here that has the beryllium-10 plus neutron, and this would be for different partial waves. So, for example, the black line is the S wave between the neutron and beryllium-10, and this is actually where the halo is. So you see now, I have the nucleon and the beryllium-10 at 20 Fermi, so it's very far, and you see it's substantially non-zero, right? So basically now, if I want to properly normalize this, I have to go up to 50 Fermi to really get, so I have non-zero values up to 50 Fermi. So that's quite amazing if you take into account that the nuclear force range is something, I don't know, 5 or 6 Fermi. So in this first or second lecture, I showed you this potential, like the argon, and basically when you get, to 3, 4, 5 Fermi, it's zero, or it's very tiny. But still, in the system, you can have, you have correlations between the neutron beryllium-10 and, at 20 Fermi and beyond. So that is what is called the halo, that you have such a large extent of these configurations. So these other curves are the D waves, so they are much more localized, right? And now if you can see the dotted line here, this is the dotted line. So that is what I get if I use only no-Korshal model. So you see, if I use only this, so I can obviously also overlap with that, and I will get this. I see that the normalization would be about the same. The peaks are much more pronounced, but you see at 7 or 8 Fermi, this is already zero. So why is it zero? Because this wave function will decay as a Gaussian. So e to the minus r square. Right, while the proper physical tail should go like this, e to the minus kr, but the k is really corresponds to the separation energy, which is very small, half an MeV. So that's why you have this huge tail in this case. And so now you can imagine why you have these differences in the E1. Right, because if you calculate with no-Korshal model, you have this kind of wave function which ends here, and the E1 is, what is the E1 operator? So it's just the R, right? So you have basically, your transition operator is E1 spherical harmonics 1 mu. So this is basically, the radius operator. So obviously this is very much affected by the long range of the wave function, and that's why there are these huge differences. And then, so one last thing about beryllium. So one can also measure so-called photodissociation. So you have, so this is maybe done from the Coulomb excitation. So you accelerate beryllium-11 and then impinge it on, for example, lead-208 at low energy, and that will disintegrate beryllium-11, and it is kind of equivalent like if you would disintegrate beryllium-11 with photons. And from that you can extract this E1 strengths. And this was done at 2 experiments at RIKEN and GSI. And so GSI data are black and RIKEN are this violet. And you see that there is some difference. But these are very complicated experiments, again, model dependent, how you extract. But anyway, so when we did the calculation of this observable, and actually our calculation agrees much better with this RIKEN measurement for some reason. Okay, so in the last 5 minutes, let me just skip a few things. And what I want. Okay, so let me now jump to the very last reaction that I want to discuss, and that I advertised already before. So I want to show you that we have, going back to this Big Bang reactions. So recently we did calculations of the helium-3 alpha gamma capture, which again is relevant for this Big Bang nucleosynthesis, as well as its mirror. So it is the triton alpha gamma going to lithium-7. So again, these are reactions which are relevant for this, and also for the so-called lithium-7 puzzle where you produce too much lithium-7. And again, this was discussed by Gabriel, and also Gabriel showed that this reaction, helium-3 alpha gamma, appears in the PP chain in the PP burning in the sun. So, so we did this calculation of that in no-core model with continuum. So Jeremy was actually the one who was leading that. And okay, so I think I want. So just to demonstrate here, if I have, the helium-3 as a projectile, the calculation is much more difficult, and one can see that, just to calculate the norm kernel. So the point is here that, you need much more information about your nuclei. So, for example, to calculate the norm kernel for this, helium-4 plus triton, you need not only one body density of your, let's say in this case, helium-4, but also up to 3 body density. So this is a very complicated object to calculate. So in this case, we can do it because we use a complete here, and so that works. But in general, it's very, very difficult, very much difficult. And so I just want to make the point that once you have more complicated, projectiles, then calculation gets much more involved. Okay, so I will skip that. And okay, so this is some of the results that we published. So it was published a few years back in PLB. And so now this is these are the phase shift of the scattering of the helium-3 on alpha. So now these points are experimental results, and then the lines again are the phase shifts that we calculated in the no-core shell model with continuum. So now for simplicity we used only 2-body interaction, because with the 3-body interaction it will be much more difficult, so we would not be able really to do it. Maybe now we could, but when we did this originally it was not possible. So we used some 2-body interaction. So we used this chiral XCLO, but then we SRG evolve it without 3-body induced. So that means it's phase shift equivalent, but it's not the equivalent to the original chiral interaction. And anyway, so with this we can actually get a decent description of of energies of these 2 states. So there are 3½ minus and 1½ minus in the beryllium-7. So I discussed it in one of the lectures before. So the spectrum of this beryllium-7 is so you have, the ground state is 3½ minus, then there is 1½ minus, and then there is a threshold of helium-3 plus helium-4, and then there is the 7½ minus, and then there is a 5½ minus, and so on. And again, if you would use this big stick code, you can calculate these energies from the no-core shell model. So in any case, we get these energies reasonably, and also properties of this ground state like the radius, moment, and magnetic moment quite reasonably. Okay, so this is what I draw here. So yeah, this is the ground state 3½ minus, 1½ minus, 7½ minus, and here is the helium-3 alpha threshold, and you see this is the 7½ minus resonance, which is here in experiment, and in our calculation it's a little bit lower, right? So we have it slightly lower compared where it should be. Here is the 5½ minus that we get more or less correct, and then this little peak here, that would be the next 5½ minus, but that one should couple to lithium-6 plus proton, which we have not included in this calculation. Okay, and so then this is the result then for this. So this is again this S factor of the capture. So that corresponds to the cross section, and you see, so there are many data. Old data here are shown in this gray, and then the new data are in different colors. So then these red ones again are from Luna. So those are the best measurements done at very low energy. So this is already like in basically in the Gamow window. And then these higher the data at higher energy are very, very, very recent. And you see that the new data disagree with the old data for some reason. And I show different calculations. The red dashed is the by Thomas Neff from GSI. So he published that a few years ago, before we did our calculation, and our result is this black line, and this blue dashed dotted line is this phenomenology when we adjust a little bit the resonance, basically the 7.5 minus we adjust, and then we get basically the bump where the data is. But otherwise it doesn't change, because this is really a non-resonant, there is no resonance there, so it's not affected by some small change. And you see, so it's not, the agreement with the data is not perfect, but it's not bad. And there is no adjustment here, right? So we get both the shape and the absolute value of the cross-section from the calculation. So it's not, we do not fit anything, we just plug in the interaction, do the calculation. Then the only thing we can adjust then is this little resonance position, but it doesn't really make any difference in where it is in this important region. And so this is, this helium-3 alpha, and then we calculate at the same time Triton alpha, and you see that, okay, so now we are higher than the data, but here is, okay, so there are also some old data all over the place, and these are the, okay, new. They are new from, I guess, 1994. And so that was a measurement. I forgot where it was done, maybe in Caltech. So that was a very decent measurement. However, you see now also the Neff's calculation is also higher than this data. So basically, all the calculations that are available, so this green is Nollet. So all the calculations that are available do not reproduce simultaneously those two data sets. So either, okay, so we are sort of in agreement with the helium-3 alpha, but overpredict the T alpha. Nollet is below the helium-3 alpha and agrees very well with the T alpha. And Neff, okay, again, Neff is again higher here, although not as much as we are. So in any case, so it seems like that there might be some normalization issues with these data. Okay, so yeah, so I'm done. So the problem is, let's say we wanted to understand why we don't agree with Neff, or at least in the shape, right? You see that the shape is a little bit different here than Neff, and I think the problem is in our calculation that our S-wave phase shift, which will be the dominant contributor in that region, is slightly higher than the phase shifts that were measured, although these have very large error bars against very old measurements. But it seems that we are systematically higher, and that's why we don't agree. So at Triumph, they decided to remeasure these to extract the phase shift in a new experiment. So I think that would be very useful for us. And what we want to do is to redo this with a three-body force to make a little bit more accurate calculation. Okay, so I'm already over, so I think I will now just conclude. Okay, so this is, okay, let me skip this. So this is now, I think I should stop, right? Because it's already, is Gabriel here or not yet? Okay, so I better stop, yeah. Okay, so this is something that's work in progress, but again, we can calculate, this S factor now. Again, this is a capture which is relevant for astrophysics, and actually now we can, this has not been measured, and we can compute this with actually very reasonable confidence. It is very complicated now, S factor, which has resonances and non-resonant contributions and so on. Anyway, so to conclude, okay, so now this was what I wanted to discuss. So if anybody is interested in medium mass nuclei, you can look at my slides that are available on the web. And so just, final words in the last 1 minute. So my conclusions in all these lectures. So I just wanted to give you some idea, what's going on in these ab initio methods for nuclear structure and reactions. And the fact is that there is a very great progress recently, not only in what I was showing you in the structure reactions with no core shell model, no core shell model continuum, but in particular in the medium masses with the new methods like coupled cluster and so on. In medium SRG, where one can really start to predict masses of nuclei or binding energies of nuclei all the way up to tin or maybe even lead. Yeah, so that's this point. And so now obviously the point is that we try to make the connection of with this many body physics and the low energy QCD, and at the same time do applications to nuclear astrophysics and other things like this fusion reactions and so on that could be relevant for applications. Okay, so now, so I have to thank my collaborators. So these are NCSMC collaborators from Livermore, Triumph. So Jeremy is now in Belgium, and TU Darmstadt. Okay. And if anybody is interested, so these are the main 3 papers where we have the technology, how this is done. So this is now recent in Physica Scripta. So there was this issue that was done at the occasion of 40th anniversary of the Nobel Prize of Bohr and Mottelson. So there's quite a few interesting articles in this issue. So you can have a look. And if anybody is interested, I have some list of books for the nuclear reactions, which I have not covered. And then at the end, I just thank you for your attention.
I don't know how was it for you, but I was thinking that for me, listening to your lecture was a little bit, like entering in the workshop of a great craftsman. And you enter and he shares with you his secret, his tricks, not only selling products that he makes, but also explaining how you get there. And also, I think I really greatly appreciate also your honesty in a sense, because you just showed not only beautiful results, but also some of the weaknesses, some of the many problems that we have in this area.
Yeah, of course.
Together with him, I think we have to also thank Jeremy very much for all the effort they made also for the afternoon session. Thank you very much.
Thank you.